The oxidative aerobic system. The oxidative system is the primary source of ATP at rest and during low-intensity activities and uses primarily carbohydrates and fats as substrates. Protein is normally not metabolized significantly except during long-term starvation and long bouts over 90 minutes of exercise. Approximately 70% of the ATP produced is derived from fats and 30% from carbohydrates. Following the onset of activity, as the intensity of the exercise increases, there is a shift in substrate preference from fats to carbohydrates. During high-intensity aerobic exercise, almost 100% of the energy is derived from carbohydrates. If an adequate supply is available, however, during prolonged submaximal steady-state work, there is a gradual shift from carbohydrates back to fats and proteins as energy substrates. Glucose and glycogen oxidation. The oxidative metabolism of blood glucose and muscle glycogen begins with glycolysis. If oxygen is present in sufficient quantities, the end product is glycolysis. Pyruvate is not converted to lactic acid but transported to the mitochondria, where it is taken up and enters the Krebs cycle, or citric acid cycle. The Krebs cycle is a series of reactions that continues the oxidation of the substrate. Begun in glycolysis and produces 2 ATPs directly from guanine triphosphate, GTP, for each molecule of glucose. Also produced from one molecule of glucose are 6 molecules of reduced nicotinamide adenine dinucleotide, NADH, nicotinamide adenine dinucleotide, NDH, and 2 molecules of reduced flavin adenine dinucleotide, FADH2. These molecules transported hydrogen atoms to the electron transport chain, ETC, to be used to produce ATP and ADP. The ETC uses NADH and FADH molecules to rephosphorylate ADP and ATP. The hydrogen atoms are passed down the chain, a series of electron carriers known as cytochromes, to form a proton concentration gradient to provide energy for ATP production, with oxygen serving as the final electron acceptor, resulting in the formation of water. Because NADH and FADH enter the electron transport chain at different sites, they differ in their ability to produce ATP. One molecule of NADH can provide 3 molecules of ATP, whereas one molecule of FADH can produce only 2 molecules of ATP. The production of ATP during this process is referred to as oxidative phosphorylation. The oxidative system, beginning with glycolysis, results in the production of approximately 38 ATPs from the degradation of one glucose molecule. 5.1 for a summary of these procedures. Fat oxidation. Fats can also be used by the oxidative energy system. Triglycerides stored in fat cells can be broken down by an enzyme, hormone-sensitive lipase. This releases free fatty acids from the fat cells into the blood, where they can circulate and enter muscle fibers. Additionally, limited quantities of triglycerides are stored within the muscle, along with a form of hormone-sensitive lipase to produce the intramuscular source of free fatty acids. Free fatty acids enter the mitochondria, where they undergo beta oxidation, a series of reactions in which the free fatty acids are broken down, resulting in the formation of acetyl-CoA and hydrogen atoms. The acetyl-CoA enters the Krebs cycle directly, and the hydrogen atoms are carried by NADH and FADH. Nicotinamide adenine dinucleotide and flavin adenine dinucleotide to the electron transport chain. An example of ATP production from a typical triglyceride molecule is shown in table 5.2. Protein oxidation. Although not a significant source of energy for most activities, protein can be broken down into the major amino acids that are oxidized in the skeletal muscle are believed to be branched amino acids: leucine, isoleucine, and valine. Although alanine, aspartate, and glutamate may also be used. The nitrogenous waste products of amino acid degradation are eliminated through the formation of urea and small amounts of ammonia. The elimination of ammonia is significant because it is toxic and associated with fatigue. control of the oxidative aerobic system. The rate limiting step in the Krebs cycle, 5.6, is the conversion of isocitrate to alpha-ketoglutarate, a reaction catalyzed by the enzyme isocitrate dehydrogenase. Isocitrate dehydrogenase is stimulated by ADP, The reactions that produce NADH and FADH also influence the regulation of the Krebs cycle. If NAD plus and FAD plus are not available in sufficient quantities to accept hydrogen, the rate of the Krebs cycle is reduced. Also, when GTP accumulates, the concentration of succinyl-CoA increases, which inhibits the initial reaction oxaloacetate and acetyl-CoA to citrate and CoA of the Krebs cycle. The electron transport chain is inhibited by ATP and stimulated by ADP. The simplified overview of the metabolism of fat, carbohydrate, and protein is on 5.7. Energy production and capacity. The phosphagen, glycolytic, and oxidative energy systems differ in their ability to supply energy for activities of various intensities and durations. Exercise intensity is defined as a level of muscular activity that can be quantified into terms of power, work performed per unit of time output. It is shown that power at maximal oxygen uptake is approximately 20 to 30% peak power on a cycle ergometer. Therefore, exercise primarily supported by aerobic mechanisms, even at 100% of maximal oxygen uptake, should not be classified as high-intensity exercise. Activities such as resistance training that are high intensity and thus have a higher power output require a rapid rate of energy supplied. They rely almost entirely on the energy supplied by the phosphagen system. Activities that are low intensity but long duration, such as marathon running, require large energy supply. They rely on energy supplied by the oxidative energy system. The primary source of energy for activities between these two extreme shifts, depending on the intensity and duration of the events, table 5.3. In general, short, high-intensity activities, resistance training and sprinting, rely on the phosphagen energy system and fast glycolysis. As the intensity decreases and the duration increases, the emphasis gradually shifts to slow glycolysis and the oxidative energy system. The duration of the activity also influences which energy system is used. Athletic events range in duration from 1 to 3 seconds, snatch and shot put, to more than 4 hours, triathlons and ultra marathons. If an athlete makes the best effort, an effort that results in the best possible performance for a given event, the time considerations are shown in 5.4 are reasonable. At no time during either exercise or rest does any single energy system provide the complete supply of energy. During exercise, the degree of which anaerobic and oxidative systems contribute to the energy being produced is determined primarily by the exercise intensity and secondly by the exercise duration. Substrate depletion and repletion. Energy substrates, molecules that provide starting materials for bioenergetic reactions including phosphagen, ATP, and creatine phosphate, glucose, glycogen, lactate, free fatty acids, and amino acids can be selectively depleted during the performance of activities of various intensities and durations. Subsequently, the energy that can be produced by the bioenergetic system is reduced. Fatigue experienced during many activities is frequently associated with the depletion of phosphagens and glycogen. The depletion of substrates such as free fatty acids, lactate, and amino acids typically does not occur to the extent that performance is limited. Consequently, the depletion and repletion patterns of phosphagens and glycogen following the physical activity is important in exercise and sport bioenergetics.
Phosphagens. Fatigue during exercise appears to be at least partially related to the decrease in phosphagens. Phosphagen concentrations in muscles are more rapidly depleted as a result of high-intensity anaerobic exercise than of aerobic exercise. Creatine phosphate can decrease markedly, 50 to 70% during the first stage, 5 through 30 seconds of high-intensity exercise, and can be almost eliminated as a result of very high-intensity exercise to exhaustion. Muscle ATP concentrations do not decrease by more than about 60% from initial values. However, even during very intense exercise, it should also be noted that dynamic muscle actions, which produce external work, use more metabolic energy than typically deplete phosphagens to a greater extent than do isometric muscle actions. The intramuscular ATP concentration is largely spared during exercise as a consequence of creatine phosphate depletion and because of the constant contribution of additional ATP from myokinase reactions and other energy sources such as glycogen and free fatty acids. Post-exercise phosphagen repletion can occur in a relatively short period. Complete resynthesis of ATP occur within 3 to 5 minutes, and complete creatine phosphate resynthesis can occur within 8 minutes. Repletion of phosphagens is largely accomplished as a result of aerobic metabolism through fast glycolysis, although fast glycolysis can contribute to recovery after high-intensity exercise. The effects of training on concentrations of phosphagens are not well studied or understood. Aerobic training may increase resting concentrations of phosphagens and decrease their rate of depletion at a given absolute submaximal power output, but not at relative percentage of maximal submaximal power output. Although researchers have noticed indications of increased resting concentrations of phosphagens, short-term 8-week studies of sprint training have not shown alterations in resting concentrations of phosphagens. However, total phosphagen content can be larger following sprint training due to increase in muscle mass. Resistance training has been shown to increase resting concentrations of phosphagens in the tricep brachia after 5 weeks of training. The increase in phosphagen concentrations may be occurred due to the selective hypertrophy of type 2 muscle fibers, which can contain a higher phosphagen concentration than type 1 fibers. Glycogen. Limited stores of glycogen are available for exercise. Approximately 300 to 400 grams of glycogen are stored in the body's total muscle and about 70 to 100 in the liver. Resting concentrations of liver and muscle glycogen can be influenced by training and dietary manipulation. Research suggests that both anaerobic training, including sprinting and resistance training, and typical aerobic training can increase resting muscle glycogen concentration. The rate of glycogen depletion is related to exercise intensity. Muscle glycogen is a more important energy source than is liver glycogen during moderate and high intensity exercise. Liver glycogen appears to be more important during low intensity exercise, and contribution to metabolic processes increases with duration of exercise. Processes increase with duration of exercise. Increases in relative exercise intensity of 50, 75, and 100% of maximal oxygen uptake result in increase in the rate of muscle glycolysis, glyconeogenesis, the breakdown of glycogen. Glyconolysis, the breakdown of glycogen, of 0.7, 1.4, and 3.4 millimoles per kilogram per minute, respectively. At relative intensities of exercise above 60% of maximal oxygen uptake, muscle glycogen becomes an increasingly important energy substrate. The entire glycogen content of some muscle cells can be depleted during exercise. Relatively constant blood glucose concentrations are maintained at very low exercise intensities below 50% maximal oxygen uptake. As a result of low muscle glucose uptake as duration increases beyond 90 minutes. Blood glucose concentrations fall, but rarely below 2.8 millimoles per liter. Long-term exercise, over 90 minutes, at higher intensities above 50% maximal oxygen uptake, may result in substantially decreased blood glucose concentrations as a result of liver glycogen depletion. Hypoglycemic reactions may occur in some people with exercise-induced blood glucose values of less than 2.5 millimoles per liter. A decline in blood glucose to around 2.5 to 3.0 millimoles per liter results from reduced liver carbohydrate stores and causes decreased carbohydrate oxidation and eventually exhaustion. Very high intensity intermittent exercise such as resistance training can cause substantial depletion of muscle glycogen, decreases of 20 to 60% with relatively few sets of exercise, low total workloads. Although phosphagens may be primarily limiting factor during resistance exercise with few repetitions or home sets, muscle glycogen may become the limiting factor for resistance training with many total sets and larger total amounts of work. The type of exercise could cause selective muscle fiber glycogen depletion or depletion of type 2 muscle fibers, which can also limit performance. Training with many total sets and larger total amounts of work. This type of exercise could cause selective muscle fiber glycogen depletion or depletion in type 2 fibers, which can also limit performance. As with other types of dynamic exercise, the rate of muscle glycolysis during resistance exercise depends on the intensity. However, it appears that equal amounts of total work produce equal amounts of glycogen depletion, regardless of relative exercise intensity. Repletion of muscle glycogen during recovery is related to post-exercise carbohydrate ingestion. Repletion appears to be optimal if 0.7 to 3.0 grams of carbohydrate per kilogram of body weight is ingested every 2 hours following exercise. This level of carbohydrate consumption can maximize muscle glycogen repletion at 5 to 6 millimoles per gram of wet muscle mass per hour during the first 4 to 6 hours following exercise. Muscle glycogen 24 hours provided sufficient carbohydrate ingestion. However, if the exercise has a high eccentric component associated with exercise-induced muscle damage, more time may be required completely to replenish muscle glycogen. Bioenergetic limiting factors in exercise performance. Factors limiting maximal performance must be considered in the mechanisms of fatigue experienced during exercise and training. Understanding the possible limiting factors associated with particular athletic event is required when designing training programs and attempting to delay fatigue and possibly enhance performance. Page 5.5 depicts examples of various limiting factors based on depletion of energy source and increase in muscle hydrogen ions. Glycogen depletion can be a limiting factor for long duration, low intensity exercise supported primarily by aerobic metabolism and for repeated, very high intensity supported primarily by anaerobic mechanisms. Of importance to resistance training, sprinting, and other primarily anaerobic activities is the possible effect of lactic acid and increased tissue hydrogen ion concentration in both indirectly and directly limiting contractile force. Several other factors have been implicated in the development of muscle fatigue that may limit exercise performance, including increased intracellular inorganic phosphate, increased ADP, and impaired calcium release from sarcoplasmic reticulum. Further research is needed to delineate the cause of muscle fatigue and the limiting factors in exercise performance. Oxygen uptake and aerobic and anaerobic contributions to exercise. Oxygen uptake or consumption is a measure of the person's ability to take in and use oxygen during low intensity exercise with a constant power output. Oxygen uptake increases for the first few minutes until a steady state of uptake, oxygen demand equals oxygen consumption is reached. At the start of the exercise bout, however, some of the energy must be supplied